So very good morning to everyone here. I'd like to begin the episode for today. It's a very pleasant Saturday morning, and I welcome you to the 53rd episode of Gyaniki Tech Talk. And today with us we have Mr. Prasanna Deshpande, who leads the e-mobility initiative for MathWorks India. In this role, he manages the automotive industry application engineering teams at Pune and in Hyderabad. He and his team members closely work with automotive OEMs, suppliers, startups, and engineering service companies in adopting e-mobility solutions through model-based design for system simulation, embedded code generation, and real-time testing. Mr. Presna brings close to 2 decades of experience in automotive industry. He actively contributes to the e-mobility ecosystem and has been a speaker at several conferences organized by industry organizations like SAE, ICAT, and IRAI. He is closely with several accelerators and startups in helping them accelerate the product development. Ms. Presna is passionate about helping professionals and students develop skills around electrification. He has also judged various student competitions. Prior to joining MathWorks, Mr. Presner has worked with KPIT Technologies Limited and Mahindra Limited. Mr. Presner holds a bachelor's degree in electronics and a master's degree in instrumentation from the University of Pune. It's a pleasure to have you with us today, sir. I welcome you on behalf of Team Gyaniki and all the participants today.
Thank you, Varshini. Good morning, everyone. Okay. Thank you, Gyaniki team, for giving this opportunity. Really feeling honored to be a part of a speaker here, and also very happy to communicate and share some of my passion with all of you people who are, I'm assuming, equally passionate about e-mobility, about electrification overall in the industry. So in this maybe next couple of next 30 to 40 minutes, I will probably talk about some of my experiences of working as a part of application engineering at MathWorks, and a couple of things before that also. The intention is maybe to share some of our learnings. It's to share some of my learnings and some of my organization's learnings also. However, not really planning to talk about MATLAB and Simulink today. That can be done later. That's not my focus today. So electrification is now definitely mainstream. Climate change awareness is increasing. Regulations have become stringent. Consumer demand is also increasing. Almost every major vehicle manufacturer in the world does have a electrification program. They either have a prototype or production or somewhere in between. They have announced either electrification of existing platforms, or they have announced new electric platforms altogether. Now, the drivers for electrification are common. Like we know the drivers for electrification, so let's not get into discussing those. However, the path to electrification varies by region, by regulation, and by customer. Some customers are interested in plugins, while some in pure EV, while many others nowadays are exploring fuel cell vehicles as well. MathWorks has been a part of this journey with many of these leaders of EV, and in our collaboration, we also observe some of the key success factors in this domain. And that is what let's begin with. Let's first understand some of our experiences with this. So this slide does have a lot of information. It does have a lot of hyperlinks also. I'll be happy to share these slides with you. But now I'm going to share some of my learnings. The top left graphic, it basically speaks about Tesla. So Tesla has been using model-based design almost since their inception, since they were a startup company. And first time we got opportunity to do some joint work with them was for their Tesla Roadster. That was an electric sports vehicle. And recently, by 2 years ago, they also published an interview where they said that they could use model-based design efficiently for improving their motor efficiency by about 6 to 8%. However, that resulted in overall vehicle efficiency improvement of 15 to 18%. So just a study how bettering design of a component affects overall vehicles performance also. And all Tesla did was actually they practiced and used newer techniques for motor control design. Of course, they are all They were always using a lot of good techniques like field weakening and all, but then they further improved it, and that resulted into excellent benefit for them. Second example is Aether Energy, our own Aether Energy. Aether Energy was a startup company long, long ago in IIT Madras, and now they have started producing their vehicles. So for Aether Energy, what we understood from Aether is how uh, they graduated from scratch, how they develop new competencies, and how they are now getting into production. They have also used model-based design to a great extent for developing several controllers. And in that link, you can find a little more about where they exactly use model-based design, what were their challenges, and what benefits they got. But what we saw is the way they approach things is really neat in terms of no crazy promises, uh, always very much focused on engineering, doing things internally, understanding challenges, and not seeking any shortcuts for their success. I think Aether is going to become a very long-term successful company. The third example is SAIC Motor. This is a Chinese company. However, their journey was basically mindset change from prototyping to production. And this is where a lot of Indian companies, in my view, this is where a lot of Indian companies are today. Building prototype is possible, and they always do that. However, for shifting from prototype to production, they definitely need to do some mindset change. They need to figure out newer ways to interact with interact with their tier one suppliers. So OEM supplier relationship can be improved. It needs to be improved because the OEM would probably want to own little more IP. OEM would want to do few more things in house than they used to do with conventional powertrains. And with this, a lot of new changes also coming. OEMs would also like to get a little bit of supplier independence. Now there are standard ways to do things. There are standard ways to share artifacts between OEMs and suppliers, and a lot of things are coming. So that's the mindset change. That's what I'm talking about. The next one is LG Chem. Now LG Chem did AUTOSAR compliant battery management system ECU as well as ISO 26262 ACLC compliant ECU for their customer. Their customer is just below them. Their customer was Volvo XC90. So Volvo XC90 is a OEM. OEM forced all their suppliers to go AUTOSAR compliant because they wanted to achieve supplier independence very clearly. So they asked LG Chem to go AUTOSAR compliant, and LG Chem also had an internal priority of ISO 26262. So for delivering the battery management system for XC90, they actually came up with AUTOSAR as well as ISO 26262 compliant ECU, and they delivered it to Volvo. Now let's talk about Volvo. What Volvo did was for managing the complexity, overall software complexity. See, Volvo XC90 is a luxury car. So it's not just a hybrid electric vehicle, which in itself is complex, but it also has a lot of infotainment and safety and other features. So they built a complete virtual prototype of their vehicle. So not just designing. While designing, every company will probably build a system level simulation model. But for verification and validation, they got detailed models of all the components from all the suppliers. They integrated, they built a very detailed virtual vehicle model and did a lot of virtual validation. That's basically front loading validation, even from HIL to desktop. And that's how Volvo did it. And they also got supplier independence by using AUTOSAR as a way to do it. So that's also a very interesting experience. And we were fortunate to be able to work with the OEM as well as with the supplier in that case. And the last example there is NIO. NIO car company is a Chinese car company. Their project was to build a cloud-based framework for SOH estimation for their batteries. However, they were a new company. They did not have so many cars in the field, so they did not have data. So what they did was they built simulation models. They used synthetic data, so simulation output as data for building their SOH-based cloud-based framework. And then as they got vehicle prototypes, their algorithm keeps on updating. That's the kind of framework NIO car company built. So different companies face different challenges, and the optimize systems and develop new competencies and mindset change and quality benchmarks, and how do they manage competency, and how one looks at continuous improvement. These are some of the things that we got to learn by working with these companies. Now let's take it one level deeper. The real challenges or challenges faced by engineers are typically role specific challenges. Now what I mean by that, a system architect cares about design trade-off studies with different component sizes and architectures. For a software architect, it's important to consider the reuse, the plug and play capability of different software companies. And a data architect cares about using data across the whole company, across the enterprise, deploy algorithms on cloud and things like that. Let's take one example. For battery, this battery system engineer or battery component engineer, he will care about modeling the battery with temperature effects, with aging effects, etc. The BMS, the battery management system developer, strives hard for generating optimized code from the BMS model. And the battery data scientist will look into predicting battery remaining useful life from the captured data from the field. So every engineer working on a component or working on a system has a different perspective of looking at the system. And the three main perspectives are these, which is system, software, and data. So meeting these challenges requires you to have a comprehensive solution. You need your tool chain aligned in this fashion, where you should be able to understand the system aspect of it, software aspect of it, data aspect of it, because the solution is going to require at least these three things. And within the system aspect also, there is going to be electrical and thermal. And then as we integrate different components together, there will be other things which are basically talking about integrating different components, and there is a whole different set of challenges that comes along with that. So that is how the tool chain that you're using needs to be. So little taking it one level further. So what is the development of system workflow for system level development? So the slide talks about learnings. Again, the slide has several links to several things. But what I am going to talk to you about is ideal workflow. What we have seen many companies, how they do system development. So there are these steps: system architecture, system performance, component development, and system validation. Now, this is at a very high level. I'm not talking about the V cycle development at this slide. That is still applicable. That is there throughout a vehicle process. But these are the main steps there. So nowadays, there is a lot of importance being given to do system architecture modeling. A lot of people are caring about model-based system engineering before doing system design, system development. Model-based system engineering, there are multiple tools for doing that. But the main value that one gets by doing model-based system engineering is you are basically able to understand requirements much clearer. You are able to understand relation between IOs of different components. That also helps you to understand if something changes in one component, where all it will affect, which all components it will affect. So that kind of dependency analysis can be done much easier by doing model-based system engineering. You can also link your model-based system engineering, your system requirements to your system design, which is probably done using Simulink. In our world, in MathWorks world, it's done using Simulink as a platform. So that is where system performance comes into picture. Now, again, that story is talking probably about Tesla only. So for system performance, I mean system simulation or system design. But instead of saying system design, I wanted to say do system design for performance analysis. You can achieve a lot of value by building vehicle simulation models with respect to system performance. By performance, fuel economy or range simulation, as well as performance simulation. And mainly what you need to do is you need to do trade-off. If you really look at system parameters, you can either achieve excellent range or you can achieve excellent performance. But in reality, you need a little bit of both. So that is what is the trade-off. That's what I'm referring to. And for that, you need to do optimization at system level. We'll talk a little more about it later. Then it is about component development. See, your tooling for system development and your tooling for component development will slightly be different because the needs are different. At system development, your battery and your motor and your power electronics, you need all of them, but you don't need to build very detailed models at that point. So that is where a battery can be used as a component, which is you drag and drop from a library, you parameterize it, and then you use it. But when it comes to component development, you might want to build a detailed battery model. That is where you might want to represent each battery cell, its electrical and its thermal characteristics, and then stack it together to build a detailed battery model. Then this model can be used, or for a motor, you can build detailed power electronics and thermal effects, switching effects, thermal effects, as well as uh, uh, power electronics, as well as thermal switching effects. So basically, these detailed models help you to design controllers, to design battery management, or to design motor controller and things like that. So that's where slightly different tooling is required. And for system validation, again, just to remind you for Volvo XC90, if you have a capability of integrating your detailed component models back into your simulation model, system simulation model, then you can build something called as virtual vehicle, which helps you to front load HIL validation at a system level to validation or desktop-based validation. So that's high level. That's a little bit of recommended workflow, or that's what we have seen a lot of EV leaders doing. Of course, achieving all this in first go is not expected. It is model-based design is always, it's like you should do one thing at a time and then improve on the in the next iteration, improve. So that's the way we recommend our customers to do. You cannot achieve everything. It's a matter of multiple years of effort. Like building a system validation model is a multiple year effort, and it's again, it's a recommended. If you really understand the thing, it's in your important and not urgent quadrant. So you don't have to do it, but if you do it, it has a lot of benefits to it. So moving on to software development, I think software design, code generation, verification, validation, plant modeling are some of the steps, are some of the things there. Software design, we have seen that there's a company called Dongfeng. Dongfeng were experts in hand coding and traditional software development workflow basically. But for their battery management system, their new project, they decided to shift to model-based design. Uh, and of course, they had to put in more efforts, but the benefits they got were excellent. Most important thing they could achieve was reuse of their software modules. Of course, their quality and their overall time for second project onwards also increased. But the most thing was reuse. So that's one of the very good learning that we had. And of course, Dongfeng is not the first company where we have learned this, that how customers can use model-based design and automatic code generation effectively. Then there is LG. LG Electronics, actually, they could make use of automatic code generation to meet and exceed their quality challenges. And that's a very interesting story. I will not spend time talking about it here, but I'd request you to go to the link and know a little more. How one can use model-based verification, validation, and code generation to improve quality metrics. And they actually went to zero bugs. That's the achievement they got. Now, plant modeling. See, we are talking about a lot of control algorithms. For verifying those control algorithms, it's good to have plant models, but you don't want to spend a lot of time building those plant models. So what do you need? You need readily available plant models, which can be quickly parameterized and used for closed loop validation. You might want to do this for a few components. You might want to do this for the whole system. Doing this for whole system will require you some expertise, some experience of doing it. So maybe a recommended way would be to start with a component and then validate a component in a closed loop fashion. You might want to call it as a model in loop or MIL validation also. And that's one of the ways to do it. And again, LG Chem, it's just to repeat and remind you about the framework of LG Chem, which is basically they used AutoSAR and ISO 26262 compliant workflow along with model-based design. Is there any question in between? I think no. Okay, no problem. Let's move on. So basically, what one needs to understand is different OEMs do work with different suppliers and different companies use different simulation softwares. What is really important here is to build simulation models as much as possible, because now we are getting into the new era of software defined vehicles. Hardware is probably becoming commodity and software is being used for differentiating vehicles and features and models and things like that. So when the software is exploding, we cannot rely on hand coding. We cannot rely on doing things the way we were doing. That is where a lot of sharing, a lot of collaboration will happen. It needs to happen. And at MathWorks, we are putting a lot of investments into developing Simulink as an integration platform. So that Simulink should be able to talk to or co-simulate with or work with multiple other tools. As of today, Simulink can be co-simulated with more than 150 tools. It is with and without FMI FMU also. FMI FMU is a common interface which allows different tools to talk to each other, to work with each other. So, okay. So you want to, everyone please check if you are muted. Okay. So just to present one thing, MATLAB Simulink has been used a lot for control system modeling, V&V and code generation. And this survey conducted by VDC in 2019, it was, they rated MathWorks as number one provider for not only for software and system modeling tools, but also functional safety and security test tools. So just to move on, one very important aspect of it is data science. Now, how do we make use of data? See, there are two extremes. One is too much data available, and second is too little data available. The slide talks about it. This thing, the Daimler fuel cell vehicle. Daimler's challenge was it was a fleet test data. So terabytes of data was getting uploaded to the clouds. And their challenge was to make use of that data for extracting the features that they wanted, and then they built a MATLAB based framework for extracting that data and making use of that data. They have done a lot of work with that data. One of the things that they did was they could figure out that data to find out optimum locations for fuel cell refueling during within the US, because they were actually tracking which vehicle is going where and how they're what are the best places for putting refueling stations. That's one of the things that did. And then the second thing we already spoke about, which is Neo car company did not have any data. So they used simulation for generating synthetic data, use synthetic data. These are the two extremes as far as too much data and no data is concerned. There are two more extremes in data science. One is, I mean, in terms of skills, one is there are domain engineers who are excellent in making productive, excellent use of data. However, they cannot really handle large amounts of data. They cannot really do AI modeling, so to say. Okay, AI is a loose term. By AI, I want to say predictive or machine learning or deep learning or related technologies. That's what we are going to refer to AI as far as scope of this presentation is concerned. So there is this domain engineers who are experienced and not so good in handling data. And the other extreme is the new generation of data scientists who are very good in handling data, who are very good in AI modeling, but they may not be really in a position to interpret that data, and that collaboration is required there. So our approach in this case is to enable domain engineers uh, to do AI modeling, to do data engineering. So domain engineers should not be required. So basically, make big data handling easy. And secondly, they should not be ensure that they don't have to do scripting. They don't have to sit and write codes because they are not going to be comfortable doing that. Um, and that's where another approach is we basically focus on complete workflow and not just the algorithm. So basically lower the barrier so that domain scientists are able to start their journey into data science. And secondly, we also focus on the whole workflow. So it's about data preparation, it's about AI modeling, it's about getting those AI models back into simulation models and simulating them, and it's also about deploying those algorithms. And for deployment, there could be embedded platforms, there could be edge devices, or there could be clouds. So the complete solution is required as far as data science is concerned. And that is also taking a lot of importance nowadays because of availability and overall sensitivity around how we can use data. One quick example to share is about BMW. Now, this was a set of domain engineers at BMW. They used they connected sensors to their vehicle and used that data to detect oversteer. And then they used machine learning for detecting oversteer. They wanted to do some control based on that. So that machine learning algorithm was converted to C code. It was deployed back to their ECU, and the complete thing was done by domain engineers at BMW. So collection of data, machine learning based modeling, deploying that into embedded device and putting it back to the vehicle. So that's the kind of solution industry is going towards. And MATLAB today definitely works with open source tools like Python. So again, it's not about using one tool. It's about using simulation, using data productively to build your solutions. So what we spoke so far, we spoke about three things: system view of looking at electrification, software view of looking at electrification, and data view of looking at electrification. However, these are not three different things. These are three main aspects of overall system design and development. Now, let us take it little one level below for working level engineers. And I'm almost done with my presentation also. But yeah, I'm going to take like five. Let's discuss for 5 more minutes. So basically, let's discuss on how simulation-based development can be used effectively for XEV, HEV or EV development. See, what are the challenges for doing model-based design for electric vehicles? We basically want to start with some benchmark. It could be existing conventional platform, or it could be a competitor platform, or it could be a set of requirements which we wish for our vehicle. Based on that, we'll go for component selection and component sizing. By component selection, what we mean, which motor should I use? Should I use a switch reluctance motor, or powder made axial flux motor, or PMSM or induction motor? There are multiple things, and in motor also there are many new options coming up. Then there is component sizing. By component sizing, yes, of course, mechanical sizing is important. But in this context, I'm referring to what should be the output of my motor to meet my requirement, and what should be the rating of my battery or size or output of my battery to be able to supply power to that motor for my range related requirements. So that's what I mean by component sizing. And the final thing is everything done, the overall all components put together, how does the vehicle look like? How does the vehicle perform to my expectations? And can this vehicle be given to uh, um, a certification agency for homologation and for getting it certified? So these are some of the challenges of these engineers who are working on model-based design for electrification. So the platform, the So typical questions that we have are basically what will be the fuel economy of my HEV or range of my EV for a particular drive cycle? How do different components behave under extreme load conditions? Will my vehicle control unit be able to handle different cases efficiently? Like there are different things to be done, like it's power management, it's mode switching in terms of regenerative braking and cruise mode. In a hybrid electric vehicle, it may have different modes like engine only mode and serial HEV mode and EV only mode and things like that. So there are multiple modes and there are multiple fault cases also. Those need to be handled by this case of thing. So what you need, again, building a EV model from scratch is time consuming. So what we need is we typically need a starting point model and some of the characteristics. Look at it in a look at it in a different way now. See what we are trying to do. We are right now we are trying to solve these problems like component sizing, component selection. So we are in top left of we are designing system design phase. In that phase, if we get a starting point EV model, so if I get a readily available model of a EV, what is my job? My job is to customize it to my needs and make it mine. So let's say I'm designing an electric two-wheeler. I have an electric two-wheeler model available. What will I do? I will look at the motor characteristics. I will change them to my motor's characteristics, close to my motor characteristics. Similarly for battery, similarly for power electronics, similarly for other transmission and tires and wheels and those parameters, vehicle mass, vehicle dynamics parameters. Everywhere I need to do that. Along with that, I also need to keep in mind that I'm either going to prepare a motor and motor controller in-house or I'm going to get it from a supplier. I need to be in a position to give my requirements to the supplier. That is where it helps one to have the model which is representing the plant and controller separately. The plant and controller separately will not probably be needed if you're giving it to the supplier because supplier is going to deliver you the motor and motor controller. However, if you're doing it in-house, it is always going to help you to have a separate plant model and separate controller model because you can use that as a starting point for your component development. Then the model needs to be open for customization and well documented. If I have to use something built by someone else, then I need to understand it better. So it needs to be well documented and it needs to be very easy for customization also. I should be able to customize it very quickly. And thirdly, the model needs to simulate fast. This is where I'm not looking for a very detailed model because detailed models have a lot of dynamics, have a lot of fidelity, they take a lot of time to simulate. However, in this case, our need is to simulate it thousands of times. And I'll tell you which use case it will get simulated thousands of times also. So that is where for iterative simulations, for working on popular HIL systems, I need the model which simulates fast. So that is the kind of modeling platform you're looking at. So you should have pre-built, I call it reference application models, starting point models, and a library of blocks, which should ideally help you to customize your models. Once you have that kind of model, it basically will help you to do these things. That model will help you to do design optimization, also verification of your vehicle control unit. So in every case, the key message of my slide is on the title of that slide. So if you just in case Saturday morning, if you miss out on something, that key message will be there on that title of that slide. So this model can be used for defining optimization problems, for defining numerical optimization problems like maximizing fuel economy of a HEV and minimizing time required for 0 to 60 kmph. This is not or now. Now we are talking about and. We are talking about that design trade-off now. Or this is one use case represented by first two bullets. Second use case is verify controller performance, the vehicle control unit's performance for different vehicle level use cases. It could be different initial SOC points of the battery for a HEV case. Or it could be different temperature conditions, it could be different altitudes, it could be different drive cycles, and a lot of things can come into picture. And it can also be used for component sizing. Like that's the third bullet, which is battery capacity. What should be my battery capacity? What should be my cell configuration? Or what if I'm using this motor? What if I'm using a motor of this size? That kind of what if analysis can be done very well once you have this kind of model. Let us take one step further just to talk to you about one example. This is one experiment we have done within MathWorks. Our problem statement was to maximize fuel economy of a HEV subject to a particular time for it's 0 to 60 miles per hour. The example that we used was a multi-mode HEV passenger car. This is a vehicle architecture of a multi-mode HEV, which is Honda Accord. Now, let me quickly explain you what is this architecture all about. In this vehicle, the engine can drive the wheels independently, the motor can drive the wheels independently, and engine and motor both also can drive the vehicles. You can see it in the right-hand side graphic. The vehicle typically starts in EV mode with the motor. Later on, it shifts to SHEV mode, and at the very efficient zone of engine, it goes to engine-only mode. The problem statement that we had was to optimize these mode switching for improving fuel economy. The solution was we developed the whole system level model by accessing parameters, by parameterizing all the components. Then we defined a numerical optimization problem using MATLAB. That numerical optimization problem was defined by using these equations, converting the curves into equations by defining these alpha, beta, gamma, zeta. And then we actually optimized, we came up with a solution which is better mode switching. Now, I have not put the result slide, but I will tell you, we could get about 3% fuel economy improvement after running the simulation for 12 hours. That is thousands of simulations on a standard laptop, on a normal my laptop, which is like Intel i5 typical laptop, not a workstation laptop. So basically, problems like this can be solved if you have this kind of model. So this gives you a rational design rationale for what you're doing. This also gives you sort of confidence that with the selected set of components, I am getting the most out of my system. And the system is also safe enough because the algorithm used in this HEV hybrid electric vehicle is using something called as ECMS control strategy for HEV. ECMS is equivalent consumption minimization strategy. So it's basically high level. See, there are two energies. There is fuel energy and electrical energy in a vehicle. This ECMS strategy helps you to normalize both of them and do the right thing. You should not be taking too much juice out of battery and you should not be overusing the fuel. You should be doing the right thing. So that ECMS talks about that doing right thing. And then with that, you could optimize it. So basically, you can do this kind of thing by building a vehicle system level model. Also, the use of vehicle system level model is that vehicle system level simulation model helps you to better understand requirements for various components. So it acts as a starting point for battery BMS. It also acts as a starting point for your motor MCU. Now this can go to your teams or your suppliers, and then they will deliver you back the other things. So this is the workflow that was used by Volvo for giving requirements to LG Chem and getting things back from LG Chem, and then integrating it back into their system level model and doing virtual validation and things like that. Now, uh, let me clarify. This is the workflow. It's my understanding of this is what Volvo did. In concept, this is definitely what they did. So that's about system level design, vehicle system level design. Now, very, very quickly, maybe next 3 minutes, let's talk about one of the challenges, which is how does a solution for modeling battery system or developing battery management system look like? See, there are 5 workflow steps. It's going to be very high level. What one needs to do is one needs to model the battery cell. One needs to model the electrical as well as thermal part of every cell. You need a capability to copy paste those cells so that and connect them to each other, stack them to each other so that you are able to build battery module and battery pack so that the electrical and thermal effects are cascaded. Then you should be able to put together some cell supervisory circuits around at different points. So measure voltage, temperature, current at different points during the battery in the battery pack and bring it ahead so that you are able to design different BMS functions. And then make use of these BMS functions, generate code, and then validate it. So these are some of the things. So this requires one to use tooling, which allows you to build electro-thermal model at a cell level. So that's the thing here. at every cell. Now, the approach that we use is we use equivalent circuit-based modeling. Understand the battery time constant, use 1 RC, 2 RC circuit, and then also represent the thermal mass and thermal conductivity, etc., etc. So if you are interested and if you have access to MATLAB Simulink, we do have a starting point model for you just to understand workflow. This model is having our battery data and you have to replace it. So not claiming that you have a very good starting point, but you can understand this model using everything. This has 16p6s configuration. And battery models, detailed battery models are useful not just for BMS design, but also for simulating things which cannot be tested on actual battery, like thermal runaway, like short to battery, short to ground, and different non-working conditions for the battery. So that's where it helps a lot. You can understand more. The MathWorks website has a lot of data related to battery management system. Of course, it is MathWorks website, so it is showing a lot of things done using Simulink, but otherwise also it is focusing on the workflow, which is applicable otherwise also. One thing to highlight is I have worked with this person, Vipin Venugopal, at Mahindra Electric. They could make use of 1D simulation very well for designing battery thermal management system for their battery packs. I think this was being used for their MESMA platform. MESMA is their internal powertrain platform for e-powertrains. Similar thing for motor also. I'm not planning to spend a lot of time. Maybe we can start discussing. I think that is also one good expectation. But to quickly say, see, for a motor control engineer, component engineer, the challenges are slightly different. How do I know if my motor controller will produce desired performance? How does the converter behave? Do they heat up too much? Once it goes to the vehicle, how does it interact with other components? So these are some of his challenges. So that is where one needs to, again, it's always a fight between what is my use case and what is the fidelity required. You should be using the right fidelity for the right use case. One fidelity is use a readily available block or use just your speed torque characteristics for representing a motor. And the other way is to build a detailed motor model, which represents power electronics, which represents thermal effects of motor for designing things for it. You can also see, excuse me. So if you're talking about motor design, then you will use something like ANSYS Maxwell or JMAG or motor design tool. You should also be able to make use of that data for validating your motor control algorithm. So that is also a need, and that also needs to be supported by the tooling that you're using for motor control design. So anyway, let's not spend a lot of time. I'll be happy to give you access to these slides for your consumption later. Will not really spend a lot of time. Again, motor control is one of our newer area of interest, and that is where we'll be happy to interact with you. End of the day, what we are looking at, or what will be my recommendation, is your eventual workflow. If I start my electric vehicle company, this is what I will strive hard for. Build a vehicle system level model, use it for component designing, and then bring in detailed component design models to build a virtual vehicle model. So to summarize, simulating full vehicle helps in doing fuel economy, range analysis, and vehicle control design and code generation. Building closed loop battery model, that means battery pack and BMS, again helps in BMS development, agile validation of the BMS ECU. And third, motor and power electronics control design workflow requires quick simulation, rapid control prototyping. Again, you need to have that kind of capability sorry, something is not right. Just a moment. I'm just summarizing. So maybe we can start with questions also. Yeah, so to summarize third point, motor control design workflow requires one to have a good simulation and rapid control prototyping capability. And I think you all use today simulation, code generation, and a lot of virtualization things. I will also be happy to connect with you, maybe over LinkedIn, if not on email ID, and know from your experiences. So thank you. Thank you, Gyaniki team, Rhythm and Shekhar for the opportunity.
Thanks a lot, Prasanna, and very comprehensive. I thought for 1 second we could just convert it from a trailer to a full day event, take it from a T20 to a 1 day, right? But obviously there is a lot more to understand as we talk through this. Yeah. Thanks a lot, Prasanna. And you can put the link on the chat window
Sure.
right now if you would like to.
Will do.
And thanks everyone for joining this morning for this lively session, and a lot to think about from the system engineering perspective, which always ends up being a gap. So lot of work coming our way. So thanks, Prasanna. Thank
Thank
you,
you, Shekhar.
everyone.